Right. Thank you for the introduction. So this talk will be of a slightly different nature than the previous ones. It will be mainly a speculative talk. So I will talk about holomorphic Fourier theory and DT invariants, which is the title of a speculative paper I wrote a few years ago. And one way to start the story is to try to address Francesco's question at the end of last time. So last time we discussed examples of correspondence between, on the one side, a quiver DT invariance, or sometimes even geometric DT invariance. So this thing has to do with counting on CY3, so either geometric Calabi-Yau threefold or this kind of algebraic categories coming from quiver with potential. And on the other side of the correspondences, we had these logarithmic Gromov Witten invariants of cluster varieties. And so here it's not about threefold, it's about some varieties in general of higher dimensions. Here the dimension of the cluster variety, so the relation between the Calabi-Yau category C and this is a log, the dimension of this cluster variety was roughly like the dimension was equal to, okay, in the quiver context it was like the number of vertices, something like the rank or some kind of K0 of C. And the kind of basic building block of these varieties was also tori C star to the power rank of K0 of C. So it's not a correspondence between invariants living both on threefolds as the usual MNOP correspondence, Gromov Witten DT correspondence, but it's a different kind of correspondence. On one side you have something which is Calabi-Yau 3, and on the other side you have some higher dimensional variety. And what will be special about this higher dimensional variety is cluster, and the way, and not only is cluster, but this skew symmetric form on the Calabi-Yau 3 side was producing a Poisson bracket here. So it's actually a holomorphic Poisson variety, and in nice cases, so if you restrict to symplectic leaves, it's really some holomorphic symplectic story. And then, so we had this correspondence at some kind of numerical level. We have some numbers equal to some other numbers. And then the natural question you can ask is that on the quiver side, on the DT side, these numbers are some kind of a shadow of some higher structures. For example, these BPS or like DT invariants. They are related, they can be categorified into a so-called BPS Lie algebra, or this kind of stack invariance we are looking at can be categorified into something called the cohomological Hall algebra. So there is a whole story which actually is some interest to some representation theorists. And so you might ask the question, what is the structure on the other side? And here the answer is this question mark, because typically in Gromov Witten theory, you do not expect the Gromov Witten numbers to have a natural kind of higher categorical lift. So it's indeed, so the point, or one of the points of this talk will be that indeed for usual Gromov Witten theory of usual real symplectic manifold, you do not expect much more than the usual story. But here, our varieties are some extra structures. They are holomorphic symplectic. And so I will be discussing this speculative picture of holomorphic Fourier theory, which will predict that indeed, on the, if you think about things like enumerative of curves in holomorphic symplectic varieties, there should be some kind of higher dimensional, like higher categorical structures, which at the end of the day should match the thing you might have on the Calabi-Yau 3 side. So there are various ways to arrive at this story. So you might try. So one way to arrive at this holomorphic Fourier theory would be to try to address this question and find this holomorphic Fourier theory picture as being the answer. I will focus on a different one, which is slightly more concrete, which actually will give a way to arrive at the answer or to guess the answer, which is to ask a different question. So in our discussion of Donaldson-Thomas invariance, a play role was, the key role was played by the wall crossing formula, which describes how the DT invariants vary when you change the stability parameter or the stability condition. So there's this kind of universal Joy Song or Concevis Sommermann wall crossing formula. And in some physics language, this wall-crossing formula is sometimes referred as a four-dimensional wall-crossing formula. The reason being that our Calabi-Yau 3, if x is my Calabi-Yau 3, from a physics point of view, we're really saying to x times R4 to produce a 10-dimensional space-time of string theory. And then our DT invariants are related to particles or black holes in R4. So this wall crossing has to do with some four-dimensional physical theory. And so the point is that you might try to compare this wall crossing story to a story which in many ways is simpler and better understood, which is a story which has many names. You might call it complex Morse theory, or Picard-Lefschetz theory, or physicists might call it Chekhov alpha, or two-dimensional wall crossing. So there is a much simpler and much better understood story. And it's known since a long time, essentially since the early days of the wall crossing formula, since some work of Joyce and then follow-up work by Bridgeland. Then there is a deep analogy between these two stories, between this wall crossing in DT theory and this kind of simpler wall crossing. So in physics language, this 4D wall crossing is very much analogous to some 2D wall crossing, but on the face of it, they are different. There is an analogy, but they are different. And the kind of question we'll try to address is it more than an analogy? Are they actually the same if you phrase things properly? And again, holomorphic field theory will be the answer to this question, at least conjecturally in some cases. So let me start by describing this simpler wall crossing story, this 2D wall crossing or complex Morse theory. So here the setup is that P be a Keller manifold and let W be a holomorphic function in P. So this pair P and W is sometimes called a Landau-Ginzburg model in the physics language. It's the kind of thing which appear as a mirror of a Fano variety. So as was mentioned in Bern's talks this morning. So the story I will describe here as for example, as a well-known analogous, if you just care about quantum cohomology of Fano varieties, there will be a story there. And here I'm describing the mirror story, which is the one involving a holomorphic function on the Keller manifold. And for a simplicity, let's assume our function has finitely many non-degenerate critical points, P1 to Pn. So I have a complicated space P, of course non-compact if I want my function to be non-constant. And I have this P1 to Pn, these critical points. And here I draw the map to C, to the complex plane. And I have some critical values, W to P1 to W Pn. And so this assumption on the critical points being very nice is like a complex analog of the definition of a real Morse function. So in Morse theory, you just have a manifold, you have a smooth function, and if the critical points are non-degenerate, you can do usual Morse theory. And here, in this complex situation where you have a holomorphic function, you might try to do a complex version of Morse theory. So what do I mean by that? So in real Morse theory, when you have a smooth function on a manifold, what you do, so you have the critical points of your function. So here's a kind of picture of critical points. And then what you do is that if you pick a generic enough Riemannian metric, you can look to gradient flow line for this Morse function. And then you might count these gradient flow lines connecting pair of critical points to cook up a complex, the Morse complex, whose generators are given by these critical points, and whose differential is given by counting these gradient flow lines. And then if you take the cohomology of this complex, you get the Morse homology. So in usual real Morse theory, the input is a smooth function on a usual C-infinity manifold, and the output is like a chain complex or a graded group. In a complex Morse theory, everything will be one categorical level up. And one way to phrase directly the answer at the final higher level is to say that so if you have this Keller manifold and you have this holomorphic function, you should be able to attach to it not just a chain complex, but something which is one categorical level higher up, which is a category. And here the answer should be the Fukaya category, or something called the Fukaya-Seidel category of this holomorphic function on this Keller manifold. And here, good point, here it should not be F, it should be W. Thank you for pointing out. So let me try to say something about what this Fukaya category is. And I will not give the standard description of what this Fukaya category is supposed to be. The standard description involves considering some Lagrangian submanifold and then doing something with them. But in a few minutes, we will try to go to an infinite dimensional setup, and it will be inconvenient to think of Lagrangian submanifold inside some infinite dimensional symplectic manifold. So instead, we'll follow a different path, which, as written here, is due to Heidis, as being proposed by Heidis, and then explored in the physics literature by Gromov Witten. It's supposed to be a kind of alternative way to think about the Fukaya category of a kind of complex Morse function. So what are we going to do? So we have this complex Morse function. And the first thing you might try to do is to reduce to a real Morse function, so reduce from a holomorphic function to a smooth function. And there is an obvious way to do that, which is just take the real part of your holomorphic function. But why the real part? You could also take the imaginary part. And in general, you might consider the real part of W over zeta, where zeta is any complex number of modulus 1. So you have a full circle of smooth functions you might extract from your holomorphic function. And if you look at one of these smooth functions, the critical points pi of the holomorphic function are exactly the same as the critical points of the smooth function. But because this smooth function comes as a real part of some holomorphic function, all these critical points are the same index in the sense of Morse theory. And so generically, there will just be no gradient flow line connecting two critical points. So in Morse theory, you have a gradient flow line connecting critical point of some index to a critical point of some index +1 or -1, depending on your convention, which at the end gives you some differential in cohomology. So it's indeed shifts the degree by 1. But here, all the points have the same index. So generically, there is just no line connecting two critical points. Like if you try to start from here and follow a gradient flow line, generically, you will go to infinity. And another way to understand why it's the case is that this gradient flow line for this smooth function are the same thing as flow lines of some Hamiltonian vector field for the imaginary part of this function. And because it's induced by a Hamiltonian vector field, the function is constant along this flow. And so this green path has to be contained in the locus where the imaginary part of that is constant. And if you draw the locus imaginary part of W over zeta where it's projected in the complex plane, it projects to some straight line in direction whose slope is determined by zeta. And so for generic zeta, there will be nothing connecting one critical point to another. But if you take a non-generic zeta, so if you pick a pair of critical points, pi and pj, and if you tune your zeta ij to be essentially the direction which connects these two critical values, so you take zeta ij to be the complex number which has the same argument as the difference between the critical values, w of pi and w of pj, then you expect to have gradient flow lines connecting the two critical points for this particular value of zeta. And so you might opt to define a number, mu ij, which is the appropriate count of these gradient flow lines. And so these numbers in the analogy I will review in a few minutes will be the analogous of the dt invariants. So here there is no Calabi-Yau 3, there is no triangulated category, there is just this setup, this function, holomorphic function. And the invariants we count as these kind of gradient flow lines connecting pairs of critical points when you tune the phase of your smooth function so that these gradient flow lines have a chance to exist. Okay, so this thing will be our key invariants. And in the physics literature, there are various names. There's something called zeta ij solitons, or count of 2D BPS states. So here the 2D is actually the same 2D as in usual mirror symmetry, is that you can consider a sigma model, so a series of maps from R2 to our variety with its potential, and these counts are counts of BPS state in this two-dimensional quantum field theory. Yes?
Just a naive question. So this 2D means, but in this picture is something maps to 2D. It's not the 2D maps to...
So which picture?
This monster picture.
Yes.
So this 2D means, I mean, in the quantum field theory, 2D maps into something.
Yeah, that's right. So here the 2D is, okay, I call P my space. So it's a theory R2 maps to C space P equipped with this holomorphic function.
Okay, so it's not the target that is the most often fixed values.
No, it's not. You mean like the C, like complex plane? Yeah, that's what it's not. Yeah.
It's not that.
Yeah, it's not that. Yeah. And so if you really want to think in this R2 picture, so here they're like particles, so it's like everything will be constant along time, so there is only R remaining. And then this flow line we are looking at is like R mapping, it's like the space R mapping inside our manifold. So like at 1 infinity, you are near the critical point Pi, on the other end you are close to the Pj, and then this gradient flow line is a soliton interpolating between them, which is some kind of localized particles in space. Okay. So you can extract these numbers, but here this picture has a natural categorification. So after all, we're supposed to reproduce a version of Fukaya category in which at the end of the day we get some category. And the Fukaya picture, the categorical structure comes from holomorphic curves. And so here the claim is that this count of gradient flow lines as a natural categorification to some kind of chain complex denoted by BPS ij, whose generators should be these gradient flow lines we'll discuss before, and whose differentials should be object interpolating between these gradient flow lines. And so they should be mapped from essentially surface. And the natural equation to impose on your surface is that it's a holomorphic curve, but perturbed by imaginary part of W over zeta. And this equation has many names. It's sometimes called the zeta instanton equation in the physics literature. And so here, this 2D is really the same 2D we discussed just 1 minute ago, which map to this 2D locus inside X. Okay. So in first approximation, you should think of that as some version of some holomorphic, or some holomorphic curve. And so this thing will define you a chain complex, which if you take the Euler characteristic should recover this count or correct sign count of gradient flow line. And if you don't only have this chain complex, but you will have operations between them which come from counting things ending in like several of these gradient flow lines. And the expectation is that if you know all of these counts, and if you put them in the correct algebraic machinery, you can output something which should recover the Fukaya category of this Landau-Gismog model, of this holomorphic function. So this story is really not the standard story. In the standard story, you have some Lagrangian, some manifold, and you define some product or infinite product by counting disk. Right here, as a kind of first step, we define these complexes which do not appear in the usual definition of the Fukaya story. And then we define operation on these complexes. And then there is some algebraic machine, which at the end of the day is supposed to give you this Fukaya category. And this picture having developed, so as being proposed, something interesting to do is some paper by Idis in the mathematical literature. And then there is this long physics paper by Gromov Witten on the algebra of the infrared, which is about, sees a way to think about the Fukaya category. And in this story, there is a wall crossing, so which is why this story should be thought as some kind of analogous to the wall crossing for DT invariants. So the wall crossing happens when you, for example, vary your holomorphic function W. So probably you need to be careful. Maybe W should remain more or less the same at infinity. But OK, apart from that, you vary W. And typically, so what will happen, so for example, the critical values of W, these points in the complex plane will move when you move W. And the claim is that at something particular might happen. So if you are in a kind of very generic situation, if you look at the critical values in the complex plane, so this thing is supposed to be a picture of the critical values, so the plane of values of W. So very generically, these 3 critical points, if I look at 3 critical values, they have no reason to be aligned. But if I move W, then in the real codimension 1 locus of some kind of space of deformations, these 3 critical points will become aligned. And so I can have this picture where the critical values for the critical point J might cross the straight line connecting the critical value I and the critical value K. And when this thing happens, you can check that the numbers we cared about previously, this number of gradient flow lines, they will jump. So it will be a wall crossing story. So the claim will be the number of flow lines which project to this line, which were contributing to this number mu ik. Through this process, there will be a wall crossing, and there will be a wall crossing formula which is roughly of this type. The idea being that in this process, you might maybe produce a new gradient flow line connecting I and K by some kind of deformation of a gradient flow line connecting I and J and J and K, and maybe it's deformed and produce something nice. And maybe this thing exists on one side of the deformation and not on the other side. So there is a wall crossing story, and there is a wall crossing formula. And if you think in classical terms, in terms of vanishing cycles of this function W, it's one version of the Picard-Lefschetz formula. In the physics literature, it's something called the Chekhotiv-Alpha wall crossing formula, or the 2-dimensional wall crossing formula, by reference to this 2-dimensional theory. And the point, and this formula from an algebraic or explicit point of view is much simpler than the one in DT theory. It only involves this formula essentially looking like that. And some related point, which is one of the reasons why the story is simpler, is that here what is a set of invariants? So it's like mu ij. So they are indexed by pairs of critical points. So if I'm in this ideal situation where I have finitely many critical points, I just have finitely many invariants. And for example, these numbers might be naturally organized into a matrix. And so you have finitely numbers to keep track of, and the wall crossing formula is simple. Whereas in DT theory, we add this invariant omega gamma, which are indexed by this gamma in some kind of Grothendieck group of some category, which is some lattice. And there might be infinitely many such non-zero such invariants. Okay, so here is a kind of analogy, which, as I mentioned, was recognized early on. Is that, okay, so on the left, I wrote something about this 2D picture I just reviewed. And on the right, I wrote something of the 4D picture. So on the 4D picture, it's related to DT theory, so the kind of thing we discussed in the previous lectures, where we start with a Calabi-Yau 3 as a geometric or categorical. And then there is this lattice gamma, some kind of Grothendieck group of the category of a numerical version of that. And then for every gamma inside this gamma, you will have moduli spaces of gamma stable object if you fix a stability condition. And a stability condition gives you in particular a number, the gamma, this central charge attached to every class gamma. And you use a phase of this number to define the notion of stability. And then you have these DT invariants omega gamma, which are counter-stable objects. And if you do things properly, these numbers may be lived to some kind of vector space level or chain complex level. And so on the other side, what we just described is if we have a holomorphic function on a Kähler manifold, so the analog of the set of gammas is these pairs of critical points, I and j. And the analog of the central charge is this difference between the critical values, WPI minus WPJ. Because it essentially sees direction, the direction of this complex number, which determines the wall closing, for example, in the same way that the stability function Z gamma determines the wall closing behavior. And then in this 2D story, the numbers we care about are these mu ij, which are counting these gradient flow lines for the smooth function rotated by the correct phase. And we discussed that in this story, actually, these numbers have a natural categorification, which are these PPS chain complex coming from counting roughly holomorphic curves. So there is this analogy. And the question we'd like to address is it more than an analogy? Can I really view the right-hand side as an example of the left-hand side? And so on the face of it, there are obvious obstructions. For example, in the ideal picture, people usually consider on the left-hand side, there is like finitely many critical points. So I will get finitely many pair of indices ij. Whereas on the dt side, I have this lattice of gamma. So at least I will need to drop this finitely many critical points issue. Maybe we need to look at some W with some infinite number of critical points. But the claim will be that even that will not be enough. So the main claim will be that the right-hand side, at least in some cases, will be an example of the left-hand side if you allow your P and your W to be, if you allow your P to be infinite dimensional. So here the left-hand side is complex Morse theory. And the claim is that we should do complex Morse theory in some infinite dimensional context. And doing that, and the claim is that there is a very natural way to do that, which will produce this holomorphic Floer theory. So one way to understand what happens is to go back to the original Floer picture of Floer theory, which at the end organized correctly produces a Fukaya category. So if you think of usual real Morse theory, you might ask, is there a natural infinite dimensional place where you should be able to make sense of it? And there is, which is simply a real symplectic geometry. So if you have M and omega, a symplectic manifold, and if you have L0 and L1, two Lagrangian submanifolds of M, then the infinite dimensional manifold you should consider is a manifold of paths. So interval 0, 1 mapping to your space, ending on L0 and on L1. And the claim is that on this infinite dimensional space, there is a natural function, which is an action functional, which is more properly defined on the universal cover of this space. And what is its definition? So if I really look at the universal cover, I look at the base path, maybe this path. And then to a point in the universal cover, it's a path from a point, a base point, to our point. But our space is a space of paths, so it's a path of paths. So we get some two-dimensional surface, and you can just integrate your symplectic form over this surface. This thing produces a function, a smooth function in an infinite dimensional sense on your space. And then you might try to do Morse theory for the smooth function on this space of paths. And formally, the critical points are the intersection points of the Lagrangians. And if you calculate what are the gradient flow lines in this space of paths, you find the holomorphic curve equation. So you find that the flow lines in the space of paths becomes two-dimensional surfaces in the original geometry. And you essentially get the Floer complex. Okay. And if you organize this Floer complex correctly, if you consider higher operations, at the end of the day, you should get the Fukaya category of your manifold. So the thing is a standard picture, which is one of the original Floer picture for what Floer theory should be, or why Floer theory is something natural to do. And now the naive thing we will do is that to suggest that we should do the same thing in a holomorphic situation. And the fact that it's something good to do for various purposes has been suggested a long time ago by Kontevi-Soberman. And here we'll kind of push it at its full categorical, like at the full categorical consequences. So we can just repeat the previous story, but instead of starting with a smooth symplectic manifold, you can start with a holomorphic symplectic manifold. So now it's holomorphic. So here there is a complex structure to start with, denoted by I. So in the previous picture, in the starting point, there is no complex structure. There is just a symplectic manifold. There is only the symplectic form. But now in this holomorphic setup, there is a complex structure to start with. And then I have a capital omega I, some symplectic form which is holomorphic with respect to this I. And now if I pick L0 and L1, two some manifolds which are Lagrangian with respect to omega I, so they are like complex and manifold, and omega I restricted to them is 0, and they are half-dimensional, then you might try to repeat the previous story. You might look at the infinite-dimensional space of paths, like usual real paths, interval 0, 1, connecting these two Lagrangians. And on the universal cover, you have this path of paths, which will give you some surfaces. And on such surface, you can integrate now the holomorphic symplectic form. And so now you get a complex valued and kind of holomorphic function on this infinite dimensional space. And so you can view this space of paths with this holomorphic function as being an example of a setup where you might try to run this story I was describing before. Okay, and so if you try to run this story, yes, that's right, exactly. So it's kind of the same space as before. So the tilde is for the universal cover. It's like for this function to be well defined, you need to go to the universal cover, else we get something multi-valued. So the point being like it's a space of paths, and maybe on the path you want to integrate a 1 form, and maybe the 1 form you want to take is a primitive of this symplectic 2 form. But this symplectic 2 form has no reason to be globally exact. And so to deal with that, you need to go through some kind of universal cover. Yeah. Yeah, that's right. So the claim will be if you do everything properly, the fact that there is a complex structure on the original holomorphic symplectic manifold should somehow induce a complex structure on this space, and this function is like holomorphic with respect to this complex structure. Yeah. And formally, you can write something which looks like a complex structure on this infinite-dimensional manifold. And so if you formally run the previous story, it should be the case that, okay, so the critical points of this function, as in usual Fourier series, they will be the intersection points of the two Lagrangians. And now in the previous story, for every pair of critical points, we were getting this number mu ij. And as this number mu ij were categorified into this chain complex BPS ij, from which you will be able to extract a category, which was the Fukaya category of this holomorphic function on P. So in the next slides, I will try to explain what this thing looks like in this infinite-dimensional setup. But if you just think that the previous story just apply, the output of this story, whatever it is, should be a category, because in the previous story, if you have a holomorphic function, the output is a category, just a Fukaya category. So here the output should be that given the two Lagrangian L0 and L1, you get a category. Whereas in usual Fourier theory, given L0 and L1, you get a chain complex or cohomology group. And now if you take all possible L0, L1 and put everything together, you might expect these categories to be put together into some kind of two categories. And I will call it footer 2 category of the holomorphic symplectic manifold. Yes?
So, are the formalized
Yeah, that's right. So the claim is that the Fleur complex should be a kind of decategorification of this Fukaya category. So there is something like the maybe like Hochschild homology or Hochschild cohomology of this category should recover the usual like Fleur. Okay, actually one needs to be. Yeah, actually this question is tricky because to talk about usual, I will discuss that in 1 minute. To talk about Fleur cohomology, we need to fix a real symplectic form. And so you need to tell me which real symplectic form do you pick, because you have some, here we don't have a real symplectic form, we have a holomorphic symplectic form. So the rough picture, okay, I will maybe not say more later, so you could consider like omega zeta, which is maybe a real part of omega I over zeta. So for every zeta, there is a usual real symplectic form. And so for every zeta, there will be a usual Fleur theory between these two Lagrangians. So you don't just get a single space, but you get kind of family of spaces parameterized by zeta. And I guess the conjecture will be that this kind of family of space parameterized by zeta provides something like the, how is it called, the kind of cyclic homology of this category, which will depend on the kind of equivalent parameter. And this thing will reproduce this family of Fleur theory group. You could say that in an even more fancier way. You can ask, from these two categories, how do you recover the usual Fukaya categories for this real symplectic form? And you could say, okay, there should be such a thing as a cyclic homology of a two category, which should be some kind of family of categories depending on one variable. And this thing should reproduce a kind of the usual Fukaya categories for this family of symplectic forms. So here I just discussed, okay, if you believe the general story, this thing should be the output, but concretely what it looks like. So like in particular in the previous story, there is this gradient flow line and this disk, this soliton or instanton, and you can ask what do they become concretely in this story. So in usual Fleur theory, there is no complex structure to start with. There is just a symplectic form. But if you pick some compatible, almost complex structure J, is defined for you a metric on your space of paths. And if you calculate the gradient flow line for this metric, at the end of the day, you get some J holomorphic curve equation. So here, one should not get confused. So here, we have a complex structure to start with, which is this I. And we'll consider J holomorphic curves, but J will be different from I. And the way to set things up is to assume that I is actually part of a hyperkähler triple of complex structure. So there is J and K, which form a hyperkähler triple. And then for every zeta, so the same zeta as before, a complex number of modulus 1, I can consider J zeta, which is a complex structure, which is a linear combination of J and K. So here is a picture to have in mind. I draw this sphere. So each time you have IJK hyperkähler triple, you have a sphere of a complex structure, AI plus BJ plus CK 1A squared plus B squared plus C squared equal to 1. And in this sphere, there is a distinguished point, which is I, which is our original complex structure. And then there is a distinguished circle, which is kind of perpendicular to this point. And I will consider complex structure J zeta, which are like points on this circle. And now what you can check, so this thing is a kind of exercise. So in the previous story, we were looking at these gradient flow lines connecting critical points. But now we're doing that inside the space of paths. And if you ask what are these gradient flow lines, so this calculation is the same one as the Fleur calculation. At the end, you get J holomorphic curves. But if you look at gradient flow line for the function real part of W over zeta, you get G zeta holomorphic curves. In particular, to calculate these numbers mu ij, or this complex BPS ij, you need to tune zeta to this value zeta ij. And the claim is that in this context, it will involve holomorphic curves, but where the complex structure is tuned to a particular value in this circle of complex structures. And if you ask what about the higher categorical level, so in the prehistory, the higher categorical level was coming from counting roughly holomorphic curve. But so now it will be holomorphic curve inside this space of paths. And so it will be a map from now something three-dimensional inside M, inside your holomorphic symplectic manifold. And if you do the exercise, what is so you think what is a holomorphic curve equation in the space of paths in terms of the original manifold. And the output is this footer equation. And actually, so in general, depending on zeta, you need to write it correctly. Here, I just wrote the kind of generic form to which it can be reduced. So it's a map from a 3 manifold to M, to your holomorphic symplectic manifold. And you have I, j, k on M, and so you can write these PDE. You can write the 3 partial derivatives of your maps with respect to the 3 variables. And then you put I, j, k in front. So actually, in the main examples I will discuss, it will be non-compact. But you might try to, okay, so as I will, okay, so because later on I will give an example of M. Okay. And the M will be, in the example, it will be like an integrable system, each in like a moduli space, as example of holomorphic symplectic manifold. But yeah, that's right. So this, I think at this level where nothing is defined, you can take any holomorphic symplectic manifold, possibly non-compact, so I think like ALE and so on, and you can ask what this story does. And I guess in almost all examples, I don't know, but yeah. Okay, so so the general picture is that this kind of two-category structure is built from holomorphic curve with respect to these hyperkähler rotated structures. And if you want to get the full categorical structure, you need to look at the solution of these footer equations. So I think Footer was a mathematician. It's like in the very early 20th century. Actually, he was a number theorist, and he was interested in the fact that spatial values of elliptic functions are really interesting for number theories, and so he was wondering if there is some hyperkähler or quaternionic version of elliptic functions, which could have number theoretic applications. And I think it never succeeded to find a number theoretic application, but along the way he wrote this kind of PDEs. And of course, the full story is speculative, and the main technical challenge, if you want to make any of that precise, is that you will need to have some control on the moduli space of this Footer equation. So for holomorphic curves, there is a well-understood story of bubbling and boundaries degeneration of holomorphic curves. But for solutions of these strange PDEs, there is no understood general behavior and general moduli space theory, which is why this story is speculative. So this speculative theory, so I wrote something in my paper, and around the same time, so Doan and Shreshnikov wrote the same speculative story, but they did more. They at least started the very first step of doing some non-trivial analysis of this PDE to say something non-trivial. So essentially, and they prove a non-trivial theorem. Essentially, they look at the case of a cotangent bundle, which is like the first case you should think about, maybe if you think in symplectic geometry. So to cotangent bundle of a holomorphic manifold with its holomorphic symplectic form, then they prove some kind of reduction theorem that this thing reduces to some kind of usual Foucault category on the zero section. So essentially, if you take some, so they prove a result which is parallel to a much older result of O and Fukaya, saying that if on a real cotangent bundle, you think of the kind of Floer cohomology between the zero section and the perturbation of the zero section, it just reduces to like usual Morse theory of the base manifold. And they prove a kind of holomorphic version of this statement that they prove that this kind of Ohm category between the zero section and a small perturbation of the zero section is just the Foucault category of the of the base manifold. So the general output of the speculative story is that if you start with any holomorphic symplectic manifold, the output should be this footer 2 category. And you should really think of this 2 category as being some A-model stories kind of made out of holomorphic curves and solution of PDE. In particular, it's a story which is different, so there are other type of speculations in the literature which attach some 2 category to holomorphic symplectic manifolds. There is something called Rosansky-Witten theory or Kapustin-Solina 2 category of brains for Rosansky-Witten theory, which is also supposed to be a 2 category, but it's a B-model category. And so actually, if you think about the 2 stories, they are kind of parallel and they are kind of obvious analogous to each other, is that if starting from these 2 Lagrangian, you produce a holomorphic function on this infinite-dimensional space of paths, there is 2 obvious things you can do. You can do the A model, which is this Foucault category, or you can do the B model. And the B model of a function is like the category of matrix factorizations. And this B model category is something which is supposed to be the output of formally doing category of matrix factorization for this function on this infinite-dimensional space of paths. Like, I mean, the same function as before. When you have L0 and L1, you produce this holomorphic function on the space of paths. And you might ask, what is the matrix factorization of this like algebraic or holomorphic function? And if you do that, the output should be a category attached to pairs of Lagrangian manifold, which maybe at the end should fit into 2 categories. And some of the B model story is somehow much older and has been discussed by various authors since long, like at least 10, 15, maybe 20 years. Whereas the A model story, even at some kind of formal level, maybe is more recent and was not really discussed before. And so one way to phrase the story, which maybe in some sense makes the whole thing obvious, is that in usual mirror-symmetry, so we're looking at this 2-dimensional series of map from R2 to some space. And here we are really looking to a 3-dimensional series from R3 to your holomorphic symplectic manifolds. And if you have a 3-dimensional series, there should be 2 categories of boundary conditions. And depending if you do some A twist or B twist, you should get one or the other. So concretely, if you replace R3 by R2 times some interval, and if on this interval you put a boundary condition coming from the holomorphic Lagrangian L0, and on the other one the holomorphic Lagrangian L1, then if you focus on the R2 factor, what you see is a series of maps from R2 inside the space of maps between L0 and L1. And then if you do usual A or B model for that, you get usual Foucault category or matrix factorizations. And so you should get a category attached to L0 and L1. Okay. So you should be able to run this story for any holomorphic symplectic manifold. And in particular, if you apply them to things like symplectic resolutions, they should play a role in this 3D mirror symmetry story. So in particular, there is some work by various people, for example, Gamage, Hilburn, Gayotto, and I think many other people, which actually probably talk about this category, but in a kind of a different language, like something closer to constructible sheave instead of Fleur theoretic language in some concrete examples. Okay, so I don't know anything about 3D mirror symmetry, so I will just end this talk by coming back to our original question, which has a link with DT theory. And so DT theory is, the story about DT theory is almost, okay, it's not 3D, but it's 4D. So because we are the Calabi-Yau threefold X, and as I was always claiming, in the physics picture, you really consider R4 times X. And so there is a 4-dimensional series here, and the DT invariants have some meaning as counting particles in this 4-dimensional series. And now somehow if I want to run the press picture out of this data, I should be able to produce some holomorphic symplectic variety. And okay, so from a physics point of view, what you would say is that you take your 4-dimensional theory and you put it on a circle. So you press R4 by R3 times S1.
What is X?
And here X is like the Calabi-Yau 3 in which you want to do DT theory. So somehow out of X, there should be a 4-dimensional theory. And if you put it on a circle, you should get a 3-dimensional theory. And then this is a 3-dimensional theory on general physics grounds should have a Coulomb branch, which would be some holomorphic symplectic manifold. So if you take some 3-dimensional theory, which is really honestly 3 dimensionals, then this Coulomb branch are the kind of symplectic singularities that Joël has been talking about. But here, because the theory is not really 3-dimensional, it's really 3-dimensional, it's really come from 4-dimensional on a circle, this thing will not be symplectic resolutions in general. Maybe there will be things which look like K-theoretic Coulomb branch in the BFN language. And so whatever they are, so they are not symplectic resolutions, but what they will be integrable systems, complex integrable systems. So actually the M will not just be a holomorphic symplectic, but because of this circle, it will come with extra structure. It will come with a holomorphic map to some base. And this thing is a holomorphic fibration. It's a holomorphic integrable system, meaning the fibers are abelian varieties.
And what is the relation between family M and the original X?
Yeah, so this thing is the good question. So I only know the answer if you decide to do DT theory for the Foucault category of X, which is related to counting special Lagrangians. Then in this case, B, like the base of this vibration, should be something like the moduli space of complex structures on X, which has dimension, okay, so roughly up to plus or minus 1, has dimension equal to the third Betti number of X, because deformation of a complex structure is controlled by some periods which come from integrating over these 3 cycles. And what is M? So M should be a family of abelian varieties, or maybe complex tori. And these complex tori should be the intermediate Jacobians of these Calabi-Yau 3 folds. So at every point, I have a Calabi-Yau 3. And from the Hodge theory of the Calabi-Yau 3, you can cook up some complex torus.
And C, the category?
And here, this thing will be a story relevant when C is the Foucault category of X.
And then you take a stub of the Foucault category of X.
That's right. So in my very first talk, I reviewed this kind of general expectation that complex structures on X should define Bridge-on-stability conditions for the Foucault category. And so indeed, to make connection with our story, it will be a key point, the base of this space should be related, let's say at least have a map to the space of stability conditions on the Foucault category. So in a purely categorical language, you should think of this structure as living above maybe some slice inside the space of Bridge-on-stability conditions. And some basic issue is that if you want not do Foucault category but sheaves, then I don't know what is M because I don't know what is B. So B is supposed to be this stringy Keller moduli space living inside the space of Bridge-on-stability conditions. In general, I don't know what it is. But if I know the mirror, then it should be the moduli space of complex structures on the mirror.
What if you start with quiver DT theory?
So because quiver DT theory is not geometric, maybe I don't know how to put it here. But okay, the basic relation with what I was describing last time is that M should be like the cluster variety. But not with the holomorphic symplectic structure coming from the cluster variety with a hyperkähler rotated version of it. And here there will be some issue, but I don't know if there really exist nice hyperkähler metrics on cluster varieties. And probably they don't, and it will be one of the multiple reasons why this story is difficult to make sense of, but definitely there are very concrete examples. Like if you run this story with this x, and if you put for this x a non-compact Calabi-Yau threefold, which is built from a Riemann surface, then this M will be the moduli space of Higgs bundles, and this map will be the Hitchin fibration.
So X will be canonically defined by the Riemann surface.
Yeah, that's also the picture is that if, let's say, you have a group G, which is ADE type, and if you care about GX bundles on C, then X will be a fibration over C in an ADE surface. So I will need to be more precise, but roughly it is what the three-dimensional geometry is. It is a family of ADE surface over the Riemann surface.
Can you do the same for some modular space of Simpson stable she's on a K3?
Ah, yeah. Oh yeah, that's right. And this M is okay.
Because
yeah, that's right.
X modular space is a local.
Yeah, that's right. And so indeed, this M will be the kind of Bovil-Mukai integrable system. Yeah, and definitely there should be a story. So the story I'm describing, there should be a special case in this compact hyperkähler situation, which it's something I think about actually. But yeah, how much time do I have? Is it like a few minutes, 2 minutes? 3 minutes, 5 minutes, okay. Okay, and so for the last connection with the cluster case, if you are in the X bundle situation, then it's known that, for example, if you look at the X bundle with poles, then when you hyperkähler rotates this complex structure, you get a character variety, which in this kind of pole story has some cluster structure by work of for Gonchar. So it is how you might connect this story to the cluster story I was talking about in the quiver case. So, okay, so here in this slide, there is some kind of way to go from a Calabi-Yau 3 setup to this integrable system holomorphic symplectic story. And now I want to recover DT theory, at least piece of DT theory from running holomorphic Floer theory for this holomorphic symplectic manifold. So to do that, I want to find some, okay, so the goal is to really realize the original analogy. There was this analogy saying DT theory look like some holomorphic function on some space. And now the main claim would be DT theory will be related to some holomorphic function on some space, and this space would be some infinite dimensional space of paths connecting two Lagrangians. So I need to tell you what are the two Lagrangians I consider in this space. And there is some obvious choice because, as we just discussed, the base is a space of stability. So, and the DT invariants depend on the stability. So if I fix stability, it's a point in the base, and so I have an obvious holomorphic Lagrangian, which is a fiber of this map. And I think to run the story, I will make this extra assumption, but at this level of vagueness, it does not matter, that there is a section for this fibration, some holomorphic Lagrangian section. For example, in the X bundle story, there is this Hitchin section, which is kind of a nice thing. And then you might try to do holomorphic Floer theory for these two Lagrangians, just section and fiber, the most naive thing. And maybe these things look boring because Floer theory is related to intersection points of Lagrangians. But here for fiber and a section, it looks like there is a single intersection point, so I will get a boring story. The story is not boring because this holomorphic function, it was essential to take this p tilde, to take this universal cover. And so there is some kind of multi-valued function with a single critical point, but if you want to make it single-valued, you need to go to a universal cover. And what is a group of this cover? It comes from the H1 of the fiber. And the H1 of the fiber, if you think of this intermediate Jacobian story, is related to H3, which is exactly the latest gamma from DT theory. So which means when I go to the universal cover, my single critical points become a lattice of critical points, which are naturally indexed. If I fix a reference critical point I call 0, they are naturally indexed by the charge lattice gamma.
Sorry, does the universal cover what?
Of the space of paths connecting these two Lagrangians. So you look at the space of paths going from here to here, and you can maybe like under some assumption, for example, if in the Hitchin case B is like a vector space, is contractible, you can ask what is the fundamental group of this space. It will be related to the pi1 of the fiber. And the key point is that the fiber is a torus, so it has a non-trivial pi1. And this pi1 is actually our lattice gamma, which parameterizes DT invariance. And so now the conjecture, and I think the conjecture as phrased only makes sense for non-compact Calabi-Yau. So in physics language, you should have a field theory, not a string theory with gravity. Then you expect your DT invariance to be related to your kind of 2D BPS states counting flow line in space of paths between these two things, which, as we argued, are related to G zeta holomorphic curves. And the claim is that the kind of correspondence we have been talking about in the last lecture between DT and holomorphic curves are kind of examples of this correspondence. But now it makes sense to lift this correspondence to one level up. If you believe that this full holomorphic first story makes sense, this thing should lift to some kind of BPS complex or vector space where in addition from this holomorphic curve, you count this solution of this footer type equation. And I would just end by one sentence. So this thing is about the relation with DT theory. You should consider these two Lagrangians. But then you might consider different type Lagrangians. For example, if you do mirror symmetry, the home between a section and itself in the usual Foucault category produce algebra of functions on the mirror. But now everything is categorical. So this home actually becomes a category. And so in this cluster language, the usual home produces the usual algebra of function on some kind of mirror cluster variety. And then you have the theta function story using work of Gross and Siebert. But now things predict that this story should be categorified. And then you might ask about comparison with categorification, which are being produced by representation theory persons. And here I just mentioned, just formally, you can write a map, which would be something like a categorification of the expansion of theta functions in a cluster chart. So if you believe this story, you can try to start to write formal things and maybe get some interesting predictions that you might try to check by other means. Okay, I will stop there. Thank you.